5.7, Part B. We're going to finish this inverses thing up here. Now, remember that you can use the graph of a function to determine whether its inverse is a function using what is called the horizontal line test. So whenever we look at a graph typically, so if I have the graph of something here and I draw it like this, okay, when I have that graph like that, I can tell if that's a function by using the vertical line test. So if I stick a vertical line out here, and let's see if it'll let me move it around. Of course it won't, but we'll do this, and maybe it will let me move it around the way I want to. I can grab and move that line anywhere along that graph, and as long as it only touches that graph in one place, it's a function. It passes the vertical line test, an up and down line. Well, whenever I do an inverse, I end up mirroring across this line right here. So what that would get me is something that looks like this going sideways. Now, if I'm looking at the blue and I do a vertical line test for that, here's my vertical line. Let's cut it out and drag it. Okay. When I look at doing a vertical line test for that, it hits in two spots all over the place. There's only one place, the very vertex, where it would only touch once. Everywhere else touches twice. That means x is repeating. I'm getting an x right here and right there. That is not a function because it doesn't pass the vertical line test. Now, I can tell that from the original if, instead of doing a vertical line, I do a horizontal line. It's been rotated 90 degrees. If I do a horizontal line test and I pull that anywhere on that graph and it touches twice, the inverse will not be a function. Okay? And that's what's kind of happening down here. So they've got an example right around here. There it is. Right around here, a little laser pointer. There we go. This is saying that the inverse of this graph is a function. It's using the horizontal line test. It passes the horizontal line test. And below it down here, what I have is that graph rotated 90 degrees. Now, that's not exactly a reflection in the diagonal, but it's close. It gives you a close assumption of what's going to happen. You can really see it here, okay? Because if I put that horizontal line on there, that inverse, when I mirror it diagonally, will not pass the vertical line test, which means it will pass the horizontal line test. It's not a function. So we can use that to our advantage whenever we're talking about these. So when it goes into this kind of a problem where it says, consider this function, f of x equals 2x to the third plus 1. So I'm going to do y equals 2x to the third plus 1. And I'm going to look at that graph, okay? And if I put a horizontal line anywhere on that graph, and I'm going to do that right now. I'm just going to say y equals b, and then I'm going to say b equals 5. Okay, so what I can do is it'll turn that into a slider, and now I can just move that up and down that whole entire graph. So if I move that anywhere on that graph, will I ever touch more than once? Well, if I highlight that one, and then I do the slider, you can actually watch as the dot only touches in one whole place. So that would be a yes. Inverses function. And then it says determine, that's the determine part. And then it says find the inverse. Okay, so I write down y equals 2x to the third plus 1. And then I just switch the x and y. You can switch the x and y at the very end if you want to, but I always find that, getting y by itself is a little easier. Whatever. Getting x by itself is fine, then switch them. Both are good. Still the same deal. Subtract 1. Divide by 2. I'll go back up here. X minus 1 divided by 2 equals y to the third. Cube root. So the cube root of x minus 1 over 2 is equal to y, or the cube root of x minus 1 over 2 is equal to f to the negative 1 of x. Where's my highlighter? There we go. These are interchangeable. F of x means y, y means f of x. And whenever we put the little negative 1 in there, that means the inverse of. So it's not just now George, a whole new equation, even though it is a new equation, but it's actually tied back into the original f, and we know that that's the inverse. That's what it takes. So determine if this one's inverse will be a function. So let's go back and we'll change it into a y equals 2 times the square root of x minus 3. Now, if you'll notice, the graph stops. It's only in the positive quadrant. So both x and y have to be bigger than 0. Okay? So as I move my slider, it only ever touches in one place. So that is okay. So let's find the inverse. So we can say yes, inverse is a function. Okay. And then we're going to say y equals 2 times the square root of x minus 3. And we're going to switch x and y. I didn't do it. It's supposed to be a y. There we go. And then we're going to get y back by itself. Set it equal to y. So I'm going to get rid of the 2 first because that's on the outside. So x divided by 2 equals the square root of y minus 3. To get rid of the square root, I square both sides. Now that 2 is going to go both the x and the 2. So I've got x squared over 4 equals y minus 3. And then I'm going to add my 3. And so my f to the negative 1 of x, or y, is equal to x squared over 4 plus 3. I could also write that as, just in case you want to know, let's see, put that out there. Technically, there's a 1 right there. So I could write it as, let's say, or f to the negative 1 of x equals 1/4 x squared plus 3. That might be how you might see it more often, so it looks more like a quadratic, an x squared plus an x plus a constant, that kind of a thing. Well, let's plug that one in. Okay, so we got x squared, it's supposed to be an x squared divided by 4 over plus 3. Now, let's do undo. There we go. Let's put both on there. So y equals x squared divided by 4 plus 3. Now, if you look at these, they are not exactly the same. The blue one only has one part of the arc. The purple one has both. Now, remember that the blue one, what kind of things can you put into a radical? Well, you can only make what's underneath there positive, right? And they had a positive 2 out in front of that. So we only need the positive things. So we need to put in a limit. And we're going to restrict the domain to where x has to be greater than or equal to 0. And now we have that mirrored image. So we were really close there, but we just need to put a little x must be greater than or equal to 0. And then we are good to go. Okay? So just be mindful of that. When you're dealing with the squareds and the square roots, or the fourths and the fourth and the fourth roots, you'll have to put some domain stuff on there because the radicals have domain restrictions. Okay? So when you're doing those inverses, be careful of that. It's going to have to be only the positive type stuff. Okay? That's what we're looking for there. Go ahead, press pause, give these a try, come back. Let's see how they go. All right, let's look at number 7. So number 7, I'm going to write y equals negative x squared. Now, it does say that x has to be less than or equal to 0. That means it's negative. I'm going to keep that in mind when my answer comes around. Okay, and we can get rid of those, but I will type in y equals negative x squared, just so I can see what the graph looks like. Let's change the color. Hold that down. Boink, make it green. Okay. So it's just pointing down. That's all it is. Okay. So switch the x and y. Get rid of the negative 1. Square root. Now, when I square root, normally I get plus and minus the square root of negative x, but remember we needed negative things. So what I'm going to do is I'm just going to erase that plus, and I'm going to keep the negative 1. And I'm going to show you why here in just a second. Let's look at the graph. If I now graph y equals the square root of negative x, okay? That doesn't have that mirrored finish to it. It has a mirrored finish for the right hand, right? It has a mirrored finish for the right-hand side of this thing, but it doesn't have a mirrored finish for the left-hand side. And so that is not the one that I'm going to need. I need to restrict. Remember, back up here, I had a restriction. So I put on my restriction, x has got to be less than or equal to 0. Okay, oop, not that one. We want it up here. Brackets, x is supposed to be less than or equal to 0. It needs to match the left arm, the negative side arm, not the positive side arm. So by doing the negative of that, now whenever I look at it, I've got that nice mirrored finish diagonally. So I need to make sure that I do the negative one. And a good way to check that is here with the graph. Now it says then graph the function and its inverse. I'm not too pushy on that, but it's not that hard. All I have to do is just take a little thing right here and go, okay? And then mine's on a grid, so it's a little easier, but if I was to put in, I got to do things less than 0. So I can put in 0. And if I put in -1, I get -1. If I put in -2, I get -4. If I put in -3, 1, 2, 3, 4, 5, 6, 7, 8, 9, I get a -9. It goes this way. And then on the other side, I'm going to do things that square root easily. 0 does, so I'll graph that in green. 0. -1 does. -1 and negative makes 1. Square root of 1 is 1. 1 times negative is -1. And then I could do -2 doesn't go very well. Neither does 3, but 4 does. 1, 2, 3, 4. The square root of -4, the square root of 4 is 2, and then it'd be negative. And then 3, I could do, well, that 5 doesn't, 6 doesn't, 7 doesn't, 8 doesn't, 9 does, so that's 4, 5, 6, 7, 8, 9. That'll turn into 3, and I just have a graph that looks like that, and it's got a mirror image, okay? Just like that. That one's gone. That one's gone. Let's do number 8, okay? Whoop, nope, that's not what I want. Stop that. Okay, number 8. We got y equals -x to the third plus 4. So let's do the consider. Y equals -x to the third plus 4. Very good. Okay, if I look at that, it's going to be an inverse. All right, so let's go ahead and switch. Then we're going to move the 4. Then we're going to get rid of the negative. So -x plus 4 equals y to the third. Then we're going to get rid of the cube by doing a cube root. So f to the -1, that's horribly done. F -1 of x. The inverse of f is the cube root of -x plus 4. So we do y equals funcs misc nth root, the cube root of -x plus 4. And there we go. We got a nice mirror. Now remember, the mirror that we're looking for is the line y equals x. I'm going to put that on there in dots in black, okay? That's our line of mirror. We want it to look the same on both sides, and to me it looks like if I folded that on that dotted line, they'd line right up. That's what we're looking for. So then I just transfer that to my graph. Ooh, excuse me. Okay, so we'll do a red one. So if I did 0, 0 plus 4 is 4. 1, 2, 3, 4. And I could even use Desmos to help me out here. 4, 0, and 1 and a little less than 2. And then there's a little hump in there. And then we'll do the green one. And that one touches at just a little shy of 2 on the 0 line and out here at 4. And it's a little loop-de-loo right there. Well, that was kind of horrible. Peaks in. No, I don't want a straight line. Oops. Green, where do we go? 1, 2, 3. Out here at 4. Turning this way. Turning that way. And if I threw that diagonal line on there, you'd be able to see that those mirror each other a little bit. I mean, I got a crappy handwriting, but, you know, That's kind of how it goes. Whoop, that's a highlighter, not an eraser. Okay, good. Everybody good? Everybody good. Good, good. And let's do number 9. Okay. Number 9, we'll do 9 in blue. So y equals the square root of x plus 2. We're going to switch. Now let's go ahead and look at a picture of it, just in case, just to help us out there a little. Oop, I don't want that line back. Let's put you back up here. Perfect. We're going to go down here. So y equals the square root of x plus 2. All right, so we have just an arc of an arm, right? And we're only positives. So we only want to do the positive part on the other side. I'm above the 0 line. So whenever I do this inverse, I only want to be the positive. So let's square this junk. There we go. Equals y plus 2 minus the 2. So f to the negative 1 of x equals x squared minus 2. So if I look at that, x squared minus 2. You can put the equals. That's okay. You don't need it, but we'll put it in there. Now, you see we get both arms, and we don't want both. I don't want the stuff on the left. I want the stuff on the right. And the stuff on the right is when x is positive. So I'm going to go with when x, hold on. I need to put my bracket, there we go. When x is greater than or equal to 0. That's going to help me out there. So I'm going to say when x is greater than or equal to 0. Put a little comma. There's my answer. And then I can make my graph. I'm just going to do it all in one color for speed. Let's see, that's at negative 2, 0. There you go. When is that? That's at 2, 2. And that's at 0, negative 2, and 2, 2. And it goes this way, and it goes that way. Has a nice diagonal switching. Okay. Very good. Right. And disappear. Let's get bigger. All right. Second to last part, main part, prove that they are inverses. This is the important part here. I'm going to do it in yellow. F of g and g of f must turn into x. Okay. So the fog and the goff must turn into x when you simplify them. So the composition, this is why we did the last section. The composition of f and g must simplify to x, and the composition of g and f must simplify to x. If it does, then they are inverses. So let's prove that these guys are inverses. First, we'll do f of g of x, the fog. So equation f, I'm going to put a nice tight parenthesis right around the x, and I'm going to fill that in. I'll color code it for you. We'll do g in green. Okay, so we're going to do, x plus 1 over 3. Now, whenever I simplify this and multiply, that's a 3 over 1 times another fraction. And when you do a fraction times a fraction, you can reduce diagonally. And so those go to 1. That leaves me with x plus 1 minus 1. And 1 minus 1 is x. So far, the fog checks out. Now we just got to do the goff. So let's do the goff. G of f of x is equal to something plus 1 over 3. That thing I'm plugging in is the f equation, 3x minus 1. And then I work on simplifying. So 3x minus 1 plus 1. I can get rid of the parentheses because there's just a 1 in front. 1 times everything is itself, so those don't even matter. So the minus 1 and the plus 1 leaves me with 3x over 3. 3 divided by 3 reduces to 1, leaves me with x. So the goff is also an x. So yes, they are inverses. Okay. Now there is a shorter way to do that, or another way to do that. And that would be simply to take the f of x equation and then find its inverse. So we switch the x and y, and then we get x by itself. And so x plus 1 divided by 3 is f to the negative 1 of x. Right, so that's the inverse. Does this match that? Yes, so they're inverses. So you could just find the inverse of one of them and check and see if it matches, or you can do the fog and the goff and be able to prove it. It will ask you to fog and goff on your work, but when it comes to the test, you can do it in the easy way. Okay, so here's a couple. Give it a pause. Try to find out if they're inverses or not. All right, here we go. Let's do number 10. I'm going to do the fog. The fog says, there's my f, something plus 5, and I'm going to plug in x minus 5. X minus 5 plus 5 is just x. That checks out. Let's do the GOF. The GOF is something minus 5, and I'm going to plug in x plus 5. And 5 minus 5 is x. That checks out. So, yes, f and g are inverses. Now let's look at number 11. Let's do the fog first. 8 times something, that nice and tight, to the third. And I'm going to plug in the third root of 2x. Well, the third root and the third cancel out, and that leaves me with 8 times 2x. That leaves me with 16x, and that's a no, because I didn't get 1x. I got 16 x's, so no, that's not it. And we can even double check that and prove it. Let's just do y equals 8x to the third, and then we'll do the switch. And then we're going to get it by itself. Divide by 8, x equals, x divided by 8 equals y to the third, and then we're going to third root it. Okay, so that's the third root, that's a 3 in the wrong place. That's the third root of x divided by the third root of 8. 2, 4, 2, and 2. There's 3 2's. So that is the third root, equals y, of x over 2 equals y. That is the inverse, and it does not match that up there. They multiplied 2 inside, and they should have divided 2 on the whole thing. And that's how they go. Last part, word problem. This is the trouble thing with word problems, and the reason why all the way back here at, sorry, where'd I go? Too far. Example, yeah, there we go. Example 1, all we did was just solve it for x. Like these, we just solve for x, and then you could do the switch at the end. You could switch x for y, and then you'd have the inverse, okay? But this is going to be similar to that situation. In many real-life problems, formulas contain meaningful variables, such as radius r in the formula for the surface area S of a sphere. S equals 4 pi r squared. In this situation, switching the variables to find the inverse it doesn't work, because area is not radius. Feet is not time. And all of those different situations, you can't interchange those. X and y are just coordinates. You can interchange coordinates, but you can't interchange feet with time. You can't interchange area with radius or distance. So what they do is they do what we did at the beginning. They just get it solved for the other letter. So in the equation here, find the inverse of the function that represents the surface area of a sphere. S equals 4 pi r squared. So we've got S equals 4 pi r squared. Do I plug in 3.14? No. Pi is a symbol, leave it as a symbol. It can just stay in the equation. It's in the equation they gave you. It can be in the equation you have at the end. So find the inverse. That means we want to isolate and get r all by itself. So we're going to undo. Next to each other means multiply. I'm multiplying by 4 and I'm multiplying by pi. So I'm going to divide by 4 and pi. I'm going to do them at the same time. So I get S divided by 4 pi equals r squared. And then I'm going to square root it. So r is equal to the square root of s divided by 4 pi. That's the inverse. I mean, you could separate it into the square root of s over 2 square roots of pi and then do multiply by square root of pi on top and bottom. So it's square root of s pi divided by 2 pi, but it's already jumbled anyway. You might as well just leave it improperly like this, okay? Then it says find the radius, find r, of the sphere when the surface area, S, is 100 pi. So all I got to do is say r equals the square root of 100 pi divided by 4 pi. Well, those cancel. R equals the square root of 4 into 100 is 25, 4 quarters, right? And the square root of 25 is 5. I don't need the plus or minus because it's distance. It's a radius. There's only positive distance. So it's just 5 feet. That's it. So when you're dealing with word problems, just rearrange it. When you're dealing with XY functions, rearrange it and then switch the X and Y. Or switch the X and Y and then rearrange it. That's how you get your inverse. Good luck.